Hi, thanks for tuning in. I'm Ainesh Bakshi from Carnegie Mellon, and today I'll be talking about low rank approximation with 1 over epsilon to the 1/3 matrix vector products. This is joint work with Ken Clarkson from IBM and David Woodruff from CMU. I'll go a bit quickly through this talk, but feel free to pause at any time and go back over what I said. Okay, so let me start off by defining the problem. In this setup, we're given as input a matrix A consisting of real numbers, and this matrix is an n by d matrix. In addition, we're given an integer k from 1 to d. And the goal is to take this matrix A and factorize it into two matrices, x and y, such that the inner dimension of x and y is k. We also want that when we multiply x and y together, the resulting matrix is somewhat close to A. For the purposes of this talk, we will focus on a more structured case of low-rank approximation, where instead of finding an arbitrary low-rank factorization, we want to find a factorization that looks like A times UU transpose, where the inner dimension of U is K. In addition to this, we want UU transpose to be a rank K projection matrix. So the operation that this projection matrix is doing is that it is taking each row of A and projecting it onto the k-dimensional subspace spanned by the columns of U. And it's easy to see that if we multiply A times U and set this to be X and set U transpose to be Y, we again get this low-rank factorization for A. So the picture to keep in mind right now is the following. We want to minimize A times UU transpose minus A. And the operation that this projection is doing is taking the vector, which is, say, the first row of A, denoted by A1, and projecting it onto the column span of U, which is denoted by the point right here. Doing this for each row and taking the difference is the objective that we would like to minimize. To recap, we can write the problem a bit more concisely as follows. We can define a projection matrix, which is UU transpose, where the inner dimension of U is K, and U has K orthonormal columns. So this defines a projection matrix. And then we can write the objective function more concisely as stated here. So we set U transpose U to be the k-dimensional identity, and we want to minimize the difference between A and A times UU transpose. We consider multiple matrix norms for this optimization problem. And in particular, we'll see results for the Frobenius norm, the operator or spectral norm, and the nuclear norm. The motivation for this problem comes from several existing works in high-dimensional data analysis. Since low-rank approximation is used as a subroutine for clustering, for topic modeling, for recommendation systems, it's also used to denoise datasets and for dimension reduction, such as principal component analysis. Since we get a low-rank approximation of the matrix, we can think of this as a data compression operation, and it also leads to faster matrix vector products. Finally, we can think of minimizing this objective on the different norms, such as the nuclear norm, as a robust variant of approximate eigenvector computation. There are several other applications that I will not go over, but feel free to check out our paper for that. So now I've described this non-convex optimization problem, and the burning question is, how do we solve it? Before I describe an algorithm to solve the problem, let me characterize what the optimal solution looks like. The optimal solution can be characterized using the singular value decomposition, where we take a matrix A, and the SVD for A is given by a product of three matrices, P, sigma, and Q transpose, where P has orthonormal columns, sigma is a diagonal matrix, and Q transpose has orthonormal rows. So how do we get a rank K matrix out of this? Well, recall that sigma is a diagonal matrix with the singular values arranged in descending order. To get a rank K matrix, we can simply truncate all but the top K. We set the rest of them to be 0, and if we multiply these out together, we'll get a resulting matrix, which is a rank K matrix denoted by A sub K. Okay, and in order to get the optimal solution to the objective as denoted here, is to pick Q sub K transpose as U transpose. And the resulting U transpose is the optimal projection. This holds more generally for any Shannon norm, which includes as special cases the Frobenius norm, the operator norm, and the nuclear norm. On the topic of Shannon norms, let me just quickly go ahead and define what these are. Intuitively, we just take the vector of singular values, which is this diagonal matrix. We consider this as a vector, and we take the p norm of this vector. So in particular, for p equals 1, we get the nuclear norm. For p equals 2, we get the Frobenius norm. And for p equals infinity, which is like the max entry, we get the operator norm. So let me now restate what we saw so far. The problem can now be defined as this low-rank approximation objective, which is non-convex, under any Shannon p norm. And the goal is to output a matrix U such that U has orthonormal columns. The optimal solution is given by the truncated singular value decomposition, but the SVD requires n times d to the omega minus 1 time, where omega is the matrix multiplication constant. So for most practical applications, this can be really slow. And the goal here is to come up with faster algorithms. Okay, before I describe any algorithm, let me talk about the model of computation that we will be considering. So the model that we'll work in is the matrix vector product model, and this provides a good abstraction for comparing algorithms, as well as proving lower bounds. In this model, the way we access the input matrix A is that we query A times a vector V1, see the resulting vector, and perhaps based on this vector, we can adaptively choose the next query, which is the vector V2, and then query A times V2, get the result, and keep repeating this process. This is a standard model for measuring efficiency in scientific computing and numerical linear algebra. And as you will see, this model is helpful for us to really understand and compare algorithms. Okay, once we fix this model, what is a really natural algorithm to try to solve the low-rank approximation problem? Let's consider a special case where A is actually a symmetric matrix, and K, the target rank, is just 1. In this case, we're trying to solve the following optimization problem. We're looking for a unit vector U, such that if we look at the difference between A and A times U transpose, this distance is minimized in, say, the Frobenius norm. So we can think of this as finding a rank 1 projection that is the closest to the input matrix A. What would be a natural algorithm to try here? I claim one natural algorithm would just be to try power method. Power method says you start off with a random Gaussian vector, you multiply A by this Gaussian vector, and you keep repeating this process t times, and you get the resulting vector, which is A to the t times g. Okay, we can then derive a unit vector from this by simply normalizing A to the t times g, and set U hat to be our approximate one-dimensional subspace on which we project. Okay, how well does this algorithm perform? In this really nice paper by Musco and Musco from 2015, what they showed is that if we set t, the number of iterations, to be O tilde of 1 over epsilon, then power method outputs a U tilde such that the cost of this U tilde is 1 plus epsilon times opt. So that's pretty nice. This says like 1 over epsilon iterations suffice. But if you're familiar with working with power method and other numerical algorithms, you might be familiar with the idea of Krylov subspaces. A Krylov subspace has a following simple idea. It says instead of just keeping the last iterate, which is A to the t times g, which is this vector over here, we keep track of all intermediate vectors as well, and stack them up to form a matrix K. So this matrix K is known as a Krylov matrix, and the Krylov subspace is simply the column span of this matrix. Then the key idea in Krylov methods is to find the best vector in the Krylov subspace. Okay, so I won't really get into the algorithm for finding the best vector, but this algorithm is fairly easy to describe. Here's a result that Musco and Musco showed for the Krylov method. It says instead of a 1 over epsilon dependence, you can save a square root factor and get a 1 over root epsilon dependence. And the resulting guarantee is still at most a 1 plus epsilon approximation to opt. This idea of a square root speedup is fairly ubiquitous in optimization and machine learning, and you might have seen it before, uh, perhaps in the analysis of conjugate gradient and so on. So at a very high level, what is going on here is that power method is computing a to the t times g, where the matrix a to the t simply powers up the singular values in sigma. So it applies the function x to the t to each of the singular values. The Krylov method analysis says we can actually approximate x to the t using Chebyshev polynomials, where the degree of the polynomial is now only square root t instead of t, and this provides a square root speedup in the total number of iterations required. Further, if you restrict yourself to the class of Chebyshev polynomials, which are the best approximating polynomials, then this degree bound is tight. So in other words, if you do try to approximate x to the t using any low degree polynomial approximation, you have to pay this square root t factor. Okay, and the central question that motivated our research is whether 1 over square root epsilon matrix vector products are necessary, or can we do better? Okay, as spoiled by the title of the talk, our main result is that you can indeed do better. And theta of 1 over epsilon to the 1/3 matrix vector products are necessary and sufficient in the STOC case where k equals 1. And the norm that we're considering is the Frobenius norm. More generally, what we show is that with 1 over epsilon to the 1/3 matrix vector products, we can get u tilde that is with probability at least 0.99, 1 plus epsilon approximation to opt. This is just formalizing the result from the previous slide. And what we also managed to show is that there is a matrix which requires omega 1 over epsilon to the 1/3 matrix vector products for any 1 plus epsilon approximation. So this result, the lower bound, is unconditional. It's simply information theoretic. And considering the matrix vector product model led us to be able to prove such a result. Note that proving such a result in RAM is not possible, and we would need to have some sort of conditional hardness if we tried to do so. Okay, more generally, what we show is for the rank k version of the problem, our algorithm requires k times p to the 1/6 over epsilon to the 1/3 matrix vector products, where p is the Schatten p norm that we would care about. And again, the guarantee is that we output a rank k projection such that it is at most 1 plus epsilon times up in any Schatten p norm. The quantification over p is that this result is true for any p greater than or equal to 1. To compare this with prior work, for p equals 2, this improves the k over square root epsilon algorithm obtained by Musco and Musco, and the k over epsilon algorithm that one could obtain using sketching. In the regime where p is between 1 and 2, there was only a sketching-based algorithm known before, which is polynomially worse in both k and epsilon. For the setting where p is greater than 2, this improves the sketching-based algorithm, which has a dependence on the dimension. So note our matrix vector products are independent of dimension, whereas the sketching version for p greater than 2 is dependent on dimension, and we improve on this result. Note that our results also translate to the RAM setting, since we can simulate matrix vector products in RAM, and these results give improved bounds even in the RAM setting. For p equals infinity, this matches the operator norm Lorenz approximation result by Musco and Musco and gets k over square root epsilon matrix vector products. I'd like to point out here that our lower bounds do not grow with k and p. So one really exciting question in this area is to obtain lower bounds that either grow with p or with k or with both. And in fact, we don't know any non-trivial lower bound for the case of p equals infinity. Okay, for the rest of the talk, I'll get into the technical details of the of our algorithm, I'll try to describe our algorithm in the special case where p equals 2, the norm that we're minimizing is the Frobenius norm, and the target rank k is just 1. I'll try to give a high-level outline of the proof, and I'll point out the challenges that appear when we try to extend to beyond p equals 2, which is the Frobenius norm case. And at a very high level, what we require is like a new variant of Pythagorean theorem for non-Euclidean spaces. I'll get to this more in a bit. Okay, so our algorithm at a very high level does the following. It optimizes over two Krylov subspaces simultaneously. So let K1 be the Krylov space that we saw before. Here we start off with a single Gaussian vector, and we iterate T1 times. Note, since our budget for matrix vector products is at most 1 over epsilon to the 1/3, we can set T1 to be just 1 over epsilon to the 1/3. Okay, great. In addition to this, in parallel, we create another Krylov subspace, where now instead of starting with a single Gaussian vector, we start off with a Gaussian matrix with 1 over epsilon to the 1/3 columns. And this matrix is capital G. We iterate this T2 times, where T2 is O tilde 1. Again, this is within our budget and as much as we can afford. So we do these two extreme parts of the spectrum simultaneously. And then we do something fairly natural. If U1 is the best vector in K1 and U2 is the best vector in K2, we take the best of the two. To formalize this, we simply just multiply U1 tilde by A and U2 tilde by A and pick the larger correlation vector as our output. And that's the whole algorithm for P equals 2 and K equals 1. We can show that the resulting algorithm does indeed give a 1 plus epsilon approximation to opt. Okay, so let me talk a bit about how we analyze this. I'm going to use as black box the following lemma. This lemma is a gap-independent bound for Krylov methods, and the gap-independent part here refers to the fact that the resulting bound is independent of how the spectrum of the matrix behaves. So it doesn't depend on the gap between the first and second or third singular value and so on. So in particular, what this says is if we run Krylov methods for t iterations, the resulting vector u tilde that we get satisfies the following property. So A times u tilde, the two norm of this, is at least the operator norm minus 1 over t squared times the times sigma 2 squared. So this gives us an additive error estimate of the top singular value. Now, how do we translate from a gap-independent bound to a low-rank approximation algorithm? So to do this, we simply use Pythagorean theorem, which says for any unit vector V in matrix A, the following is true. So A minus A times VV transpose is actually equal to the Frobenius norm of A squared minus the Frobenius norm of A VV transpose. And this is simply because this is an orthogonal projection. VV transpose is an orthogonal projection matrix. We can simplify the second bound to just be A times V LT norm squared. And now it's fairly easy to see how to use Pythagorean theorem. We just apply it to A times U tilde. Here I've done this calculation explicitly, so we can write using Pythagorean theorem the following decomposition, and then we simply use our lower bound from the gap-independent lemma to show that we get an additive error of 1 over t squared times sigma 2 squared. Setting t to be 1 over square root epsilon recovers the result from Musco. Okay, so this is one part of the analysis. The next thing that we will use is a gap-dependent bound. Note that this bound actually depends on the singular value gaps. And this is where we really use the fact that we are starting off with a block matrix instead of just a column of a column vector in the second Krylov matrix. And this says that if we start off with a matrix of size B, so if our random matrix has B columns, and we iterate for t iterations, then we get the following additive error guarantee. We get 1 over 2 to the t times the gap between sigma 1 and sigma b. So as we increase B, we can exploit gaps between larger and larger parts of the spectrum. Okay, so the corresponding picture to keep in mind here is the following. So let's say sigma 1 and sigma B differ by a fixed constant. Then what this gap dependent lemma says is that the convergence as a function of t is exponential. Okay. So what we now do is we combine the two bounds that we saw for the gap independent and the gap dependent case as follows. So we say that either there is a constant gap between sigma 1 and sigma b, where b is set to be 1 over epsilon to the 1/3. This we chose carefully. Either this is the case and we get exponential convergence, or the objective value itself is large as a function of epsilon, and we can get away with a less accurate solution. Okay, so this is a lot to process, but the picture I like to keep in mind is as follows. So let's say we are in the case where our matrix A is simply a diagonal matrix, and after 1 over epsilon to the 1/3 singular values, there is a gap of a fixed constant. So in particular, there's a gap of a half here. So we have all ones, and then the last 1 over epsilon to the 1/3 singular value is a half, the rest are 0. Okay, in this case, if we run the gap dependent bound, after say log n iterations, we get additive error that is going to 0 really quickly with a number of iterations. And this case is fairly easy. Okay, so let's consider the opposite case. In this case, there is no gap in the top 1 over epsilon to the 1/3 singular values. They're all 1. But now observe that our objective value, which is essentially the sum of squares of all of the singular values from the second one to the 1 over epsilon to the 1/3 one is 1. So this objective value itself is 1 over epsilon to the 1/3. If we want an additive epsilon times up approximation, we only need additive error, which is epsilon to the 2/3. And this we can get by simply running the first original gap independent bound for 1 over epsilon to the 1/3 iterations. Okay, so now let me say a few words about going beyond Euclidean spaces. The main obstacle to go beyond Euclidean spaces is that there is no Pythagorean theorem for projection matrices when we change the norm from Frobenius norm to any Shannon P norm for any p not equals to. So as a first step, we don't even know how to analyze this quantity, which is A minus A times U transpose under any Shannon P norm. So our main technical contribution here is to come up with a generalization of the Pythagorean theorem to the setting where p is any p which is greater than 1. In particular, what we show is a one-sided Pythagorean theorem, and it doesn't really type check with the kind of result that we saw before, but it says the following. For any unit vectors u and v, we have that the Shannon P norm of A is at least the Shannon P norm to the P of VV transpose, so this is the projection onto V, times the projection onto U, plus the projection away from V and the projection away from U applied to A. What we've managed to show is that this asymmetric guarantee suffices for our purposes, and we can derive the results that we need using just this bound. Of course, we show a more general version of this statement, where U's and V's need not be rank 1 or just a simple unit vector, but rank K projection matrices. Okay, and the main tool that we use to prove such a bound is pinching inequalities by Bhatia, Kahan, and Lee, which say the following. So if we look at our input matrix A and interpret this as a block matrix, so the form A1, A2, A3, and A4, then we can relate the Shannon P norm of different blocks to the Shannon P norm of the entire matrix. And this kind of bound helps us prove this one-sided Pythagorean theorem that we need. For more details on this, I recommend taking a look at the paper. Okay, so I'm going to conclude with some takeaways. At a very high level, our results indicate that we can go beyond Chebyshev-style square root speedups by exploiting more structure in the problem. We would be very curious to see if this phenomena occurs in other problems as well. Sometimes it's nice. Sometimes non-Euclidean spaces can also have nice geometric properties, like approximate Pythagorean theorems, even if they don't satisfy Pythagorean theorem exactly. And we can use these to our algorithmic benefit. Tools like pinching inequalities for operators can be applied to other problems. Our tools are fairly general, and we provide a bunch of new such tools from linear algebra. The matrix vector product model is useful to compare algorithms since it's easy to prove unconditional lower bounds in this model. And finally, I'll leave you with this open question of the matrix vector complexity of spectral or operator lower rank approximation, which is the p equals infinity case, where we don't have any non-trivial lower bounds as of right now. Okay, thank you.